Now we will go ahead and learn about the synthesis and reactions of amines. So let's look at some of the synthesis first. Some of these you have done before, so hopefully they'll keep coming back to your mind as we are going through all of this. The first one is using SN2 reactions, okay? And so in SN2, of course, you have to have a substrate, you have to have a nucleophile. So the substrate is an alkyl halide, whereas the nucleophile now can be an amine. So depending on what you're trying to make, and choose different kinds of amines. If you want to make a primary amine, then you would choose ammonia. If you want to make a secondary amine, you would choose a primary amine. If you want to make a tertiary amine, you would choose a tertiary amine. So which means really all you're doing here with the substrate is you're adding on an R group, okay, to it. So in case of the primary amine, no problems, because yes, you are making an amine. But in the other cases, you are already starting with one amine and then you are adding another R group to it. Okay, so it's a very nice, simple, straightforward reaction. The first product that you end up getting is a salt, which then you can deprotonate, treat that with a base, deprotonate the salt, and then get your amine. Okay, so you can make primary, secondary, tertiary amines. And if you wanted to make a quaternary amine, then you can do that too. And this is useful when you're trying to make those arylamines, okay, for example. So that's when this reaction is really helpful. As simple as these reactions seem, they're actually not very good reactions, okay? So it might seem very straightforward. Oh, I can go ahead and do one substitution and I can get a primary amine. But if you look at that, the primary amine can then go back and react again with the alkyl halide and continue on, and then the secondary amine can go on, react with another halide. So what is stopping it from reacting? Absolutely nothing. You can try to have a little bit of a mole ratio control, but honestly, there's nothing stopping it from giving you primary, secondary, and tertiary amines. Okay, so you can have multiple alkylations, and so then you really are defeating the point of the synthesis. So this synthesis would be, for example, the best if you want to make a tertiary amine. Okay, because in tertiary amines, you don't have to have the primary or secondary. You can go all the way and substitute all the hydrogens, okay, or for making quaternary amines. So it has its usefulness, but not for primary and secondary amines. Using azide is a little bit better than using SN2. Now, azide also is kind of an SN2 mechanism. So you still have your substrate, and then the azide is going to be your nucleophile. Azide is this compound here, this ion, which is 3 nitrogens. Okay, and so this is called an azide. It does not exist by itself, obviously. N3 will exist with something else. So for example, sodium azide, potassium azide, something like that. And so once you add an azide to your alkyl halide to an SN2 reaction, you get an azide as the product, okay, of that substitution. And then you can go ahead and reduce that to give you an amine, okay? And so this is how this reaction will work. Here is another example of using azide as a nucleophile, and these reactions work fine, no problems. You can get a nice primary amine. There is only one little issue with azides, and the fact is that they are actually a little bit explosive, okay, which means that they are little sensitive, okay, to motion, okay, and so one has to be really careful working with them. Otherwise, they're really good, okay, to make primary amines. But here is the best synthesis for primary amines, really. Using Gabriel synthesis is the best. Okay, so what we do is we use what is called a pthalimide, and pthalimide is coming from phthalic acid, which is a carboxylic acid, and here's the amide linkage, hence pthalimide. And what you do is you treat that with potassium hydroxide, okay, and you get this reagent, which is the Gabriel's reagent. Then you can do an SN2 reaction on this, okay. So now again, you choose your alkyl halide, and you do an SN2 reaction on this, and then don't worry about the mechanism, and then eventually what you end up getting is a primary amine, okay, in this case. So that's how it works. This, by the way, is hydrazine, okay, NH2, that's hydrazine, and so once you add a hydrazine to it, this will cleave this group over here, and then once the hydrazine will bond with the carbonyl carbon here, your primary amine is released. So Gabriel synthesis is really one of the best ones to use for primary amines. There are some other ones too, but this is one of the best ones. I need you to remember the Gabriel reagent. Okay, so if I give you this, then you should remember that this is a Gabriel's reagent and not really a starting material for your reactions. Okay, and say what it means. Okay. So this next synthesis is called reductive amination, and this one we have kind of done before, but not completely, okay, at least not as far as synthesis of amines is concerned. So this is reduction of imines from aldehydes and ketones, and so I wrote this reaction here just to kind of remind you what happens. So here's cyclohexanone, you treat that with ammonia, and this is what you get, it's an imine, okay? And so remember, with primary amines and ammonia, this is what you will get, which is a double bonded nitrogen. It's called an imine or a Schiff's base. If you treated the aldehyde or a ketone with a secondary amine, you would get an enamine, okay, which had a double bonded carbon-carbon bond, okay? So which means that the nitrogen amine group was already there, all right, to begin with. So anyhow, these imines are what I'm talking about. So go back to aldehydes and ketones and you will find this reaction there. And so you can take any derivative of ammonia now, okay? So ammonia here, primary amine, secondary amine also you can take. You can't take tertiary. Tertiary will not react. But primary and secondary, and then of course ammonia, you can take all of those. It will all give you imine or enamine, and then you can reduce all of them to give you amines, all right? Depending on what kind of a ammonia derivative that you use, you will get that kind of amine. So if you use ammonia, just simple ammonia, then you'll get a primary amine. If you use a primary amine, you will get a secondary, and so on and so forth, okay? So here are some examples of how this is actually done. So this one is primary amine, okay, of course, with the benzaldehyde, and you're using just ammonia. The hydrogenation here that's going on, that is the reduction step. Now, depending on what kind of functional groups you have around, you can use any reducing agent. You can use hydrogenation, you can use lithium aluminum hydride, you can use sodium borohydride. This one here is a borocyanohydrin, so you can use that one as well. So any kind of a reducing agent would be fine. Just make sure you find the hydrogen in there somewhere. And as soon as you know that there is hydrogens in there, then of course you have the reducing agent. All right, so this is to make primary amine here. If you take a primary amine, that will give you a secondary amine with benzaldehyde. If you take a tertiary amine over here, excuse me, a secondary amine here, then you would get an enamine, and then when you reduce that, you would end up getting a tertiary amine. So you can get all of these different kinds of amines using the reduction of imines. So yeah, it's a very good synthesis and exactly of what you want to make primary, secondary, or tertiary amine. Here is reduction of nitriles, oximes, and amide. And if you remember again back from aldehydes and ketones, it's the same thing that we did before also, okay? When you made oximes and some of the other derivatives that you made, you can take any one of those and you can reduce them, okay? And so that's what this is. The general reactions for all of these reductions are that if you have a nitrile, you can reduce them. And remember, we just finished nitriles and carboxylic acids also. So here is a nitrile. If you reduce that, you will get an amine. You reduce an oxime, which you get from hydroxylamine, then you will again get a primary amine, and then if you take an amide and you reduce an amide, you get a tertiary amine or a secondary amine, whichever one, whatever the substitution is on the nitrogen. Okay, so you can take almost anything and reduce it. I hope you're seeing a pattern over here, because when we were talking about carboxylic acid, everything was oxidation, 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 because carboxylic acids are the most oxidized of all functional groups. But with amines, hopefully you are seeing the pattern of reduction, reduction, reduction. Almost everywhere we are trying to do reduction, you can take almost any group and reduce it. Okay, so here are some examples of the reduction then. So here is oxime, here is a nitrile, and here is an amide. Okay, and you can reduce that. So just keep in mind, what kind of amine would you get? Would you get a primary amine or a secondary amine or tertiary amine? So keep that in mind going through all of these reactions. Also keep a note of all of these different reducing agents that you see here, okay? One of the biggest problems is, of course, recognizing reagents in organic chemistry. So hopefully you're keeping a list of all the reagents. So the next reduction is reduction of nitrobenzene, and we've done this before when we were talking about aromatic compounds. And so this is the general reaction where you take a nitrobenzene, treat that with hydrogen with a catalyst, or you can also use iron with HCl or tin with HCl, and you can get aniline. Okay, so here is an example of this reaction. So again, you've done this before also. Okay, so it's nothing new. What is new is right here, okay, with the Hofmann rearrangement. The Hofmann rearrangement is a neat reaction. It's only for making primary amines. You can't make any other kind of amines from this one. And in this case, you always start with an amide. Okay, so you start with an amide, you treat it with bromine and sodium hydroxide, and here is the reaction, okay, for it. So you treat it with bromine and sodium hydroxide, and you end up getting RNH2. So what happens really in this reaction is that you lose this carbonyl, okay, over here. So which means for Hofmann rearrangement, you have to remember that you will lose one carbon, okay, when you try to do these syntheses. And as we're going through all of these syntheses, hopefully you're keeping a note of that, okay, where you're adding a carbon, where you're losing a carbon. Here you are losing a carbon, okay, when you do the rearrangement. So the product is your primary amine. You have sodium bromide, sodium carbonate. This is where the CO went, and then water also, okay, is part of the reaction. The mechanism is not required, but it's very interesting. Here is the mechanism of the Hofmann rearrangement, and it's go through it one by one and see how this works and where everything is coming in and going out, especially how the C double bond O, the carbonyl, how does that go away? Okay, and this is a new species, isocyanate, that you've never seen before. So that forms, and then that, you know, causes the release of carbon dioxide and so on. Okay, so it's a really interesting mechanism of how you end up getting a primary amine from an amide. Now for the reactions of amines. Amines are so different from what we have done so far that the reactions are also quite unusual. The first one will be familiar to you because we talked about it in aromatic chemistry. So this is not really a reaction of the amine group. This is a reaction on the benzene ring because of the amine group. Because if you have an amine group on the benzene ring is highly activated. Okay, and so you end up getting multiple brominations, alkylations, whatever it is. Well, no, it doesn't do fetal alkylation or acylation, but you get multiple halogenations if you're using halogen. So this is not really a reaction of amine, but this is a property of amine that you should not forget, okay? The next reaction is Hofmann elimination. Yeah, we just did Hofmann rearrangement, and now this one is Hofmann elimination, okay? And so this is really interesting because what it does is it gives you an alkene from an amine. An alkene from an amine means that you have to eliminate something, all right? An alkene from an amine also means that you're losing the amine group, okay, which really is a terrible leaving group, all right? So how do you make amine, which is NH2 minus, you know, a good leaving group? And this is done by adding methyl iodide, okay, excess of this. So Hofmann elimination will generally give us also Hofmann product, which really is the opposite of Zaitse's product. Okay, remember Zaitse's product was when you get the more substituted alkene. In case of Hofmann elimination, you will always end up getting something that is not so substituted. Okay, so which means that non-Zaitse's product or Hofmann product as we call it. So what happens in this case is when you have an amine like this, like a secondary amine, and if you treat that with methyl iodide and you keep treating it with methyl iodide, excess of it, so in that case, your nitrogen is completely alkylated and forms a quaternary salt. That was the reaction we did a few slides ago. And then you treat that with an oxidizing agent. And so what it does is it eliminates this amine, okay, over here. So once this is eliminated, that's how you get the alkene. And why do we get this alkene versus the Zaitse's product? This is because this is a bulky group. Okay, the nitrogen that you end up getting over here, these are all substituted nitrogen. So if it's highly substituted nitrogen, then the elimination cannot occur from an internal carbon. The elimination has to occur from the outer carbon, okay, the terminal carbon or the more accessible carbon. So this hydrogen is more accessible than the internal one, and so therefore you end up getting what's called Hofmann's product. So this is a neat way of making an alkene from an amine. Now, one of the most interesting reactions of amines is with nitrous acids. Okay, now this is nitrous acid, it's not nitric acid. Okay, nitrous acid is HNO2, nitric acid is HNO3. So nitrous acid is actually a weak acid, is not as strong as nitric acid, and it's usually prepared in the lab by using sodium nitrite, which is NaNO2, and sulfuric acid or hydrochloric acid, usually hydrochloric acid, and concentrated for that one too. So here is HCl with NaNO2. Again, remember this is not nitrate, it's nitrite. Okay, so sodium nitrite with HCl, and it gives HNO2. We write it like HONO, also called HONO, if you want to call it that. And then you also get a salt. Okay, so this is generated. And the thing about these acids, okay, the nitrous acid is that it is generated in situ. It means that as soon as you have to use it, you have to make it right then. Okay, so you be ready for it. It cannot be stored. It is unstable, and so it will start reacting with water right away. So you have to use it right away. Okay, within like 5-10 minutes of making it. So generally, what we say is that we are generating it in situ, or we're going to use it right away. And sometimes when you see it in reactions, you will actually see it in square brackets, which tells you that you have to generate this. It's not a stable acid or a stable chemical, all right? Or you will see the entire list of chemicals in there, okay? But you know that if you have this kind of a combination of chemicals and conditions, then you're making nitrous acid, okay? So you have to remember these things. The acid also has to be made at a really low temperature. So it's not really low, it's like, 0 degree, which you can in an ice bath. So this is what you generate, nitrous acid, and these nitrous acids can then react with the secondary and primary amines. What I've given you here with the tertiary amine is that, again, it does not really react with the amine, it reacts with the aromatic ring. Okay, and so the tertiary amines that are aliphatic don't even react, okay, with nitrous acid. But even the tertiary amines, okay, will not react with nitrous acid. See, the amine is still there. What has reacted is the benzene ring. Okay, so you end up getting this nitroso functionality on the benzene ring. So if this is what you're trying to make, this is fine. Okay, otherwise tertiary amines really are not that exciting with nitrous acids. The secondary amines, however, they do a reaction with nitrous acids, and in that case, you will get these kind of compounds, which are called the N-nitroso compounds. So now you do get the reaction on the nitrogen. This is acid-base reaction going on over here. These compounds also actually have no function as far as organic chemistry is concerned. They are studied a lot more for their toxicity. Okay, and we'll talk more about this in the class also. But N-nitroso compounds are considered to be very potent carcinogens, and in some cases they may actually occur in our foods and all. Okay, so we will talk about this in class. But in any case, this is what happens when you have a secondary amine, okay, with nitrous acid. Again, not very useful reaction, which gives you a hint that I will probably never ask you this in the exam. However, nitrous acid with primary amines is a whole different ballgame. Okay, and so now in this case, you actually get very good reactions. So here's what happens when you have a primary amine with a nitroso ion. Okay, the nitroso ion is coming from the nitrous acid. So once this forms, you end up getting a diazotic acid. Don't worry so much about the mechanism. Come right here, and again, this is something intermediate that forms. Come right here. This is the diazonium salt, okay, or the diazonium ion that we end up forming. The diazonium ion is very interesting ion, okay, because what happens is that this N2 that's created over here, diazonium, okay, dia means two, azo means nitrogen. So we have two nitrogens that are connected to each other. The last time you saw this was an azide when we were doing the synthesis of amines. So azide is where you saw this, all right, and this is called diazonium ion over here. So this is actually ready to leave. I said to you before also that these are actually very unstable kind of molecules and compounds, and so this is ready to leave, and as it is ready to leave, it generates a carbocation, okay, and this is what is interesting about this, okay. So here what you've done is you've taken an amine, which is a primary amine, and generated a carbocation from it. The way you would generate a carbocation from an amine is by making the amine a leaving group, which if you think in normal terms of SN2 reaction, you would have NH2 minus as a leaving group. So yet again, NH2 minus, not a good leaving group, terrible leaving group, okay? So which means that it's not going to go. So this is a very good way to make it go. So if you want to do reactions on amine, you can. You just have to use this method, okay, to do substitutions on amine. Otherwise, nobody does substitutions on amines because amines are terrible leaving groups, okay? And so once you generate a carbocation like this, then you can have any substitution reaction going on. On the next slide. So here we have, okay, an amine. So again, this is a primary amine, okay? We will not take secondary and tertiary, of course, don't even react. So this is a primary amine. Treat that with the nitrous acid that's generated over here. And then you end up getting the substitution, okay? Now, in this case, this is a little bit weird substitution given to you because if you see that you have a substitution with chlorine with alcohol and then you also form alkenes, and that is a problem with primary carbocations. If you remember, primary carbocations are not very stable. So, which means you can get substitution, you just, will get something else also. So if there is hydrochloric acid in there, you will get the chlorinated product because the chloride would be your nucleophile. You would also get some alcohol because water is present in there. And then you might also end up getting some alkenes, which is elimination reaction. Okay, and so which means that it's not the best thing to do with the primary amines like this, where rearrangements and all of this thing is possible. So it doesn't have that much of a functionality, okay, not with primary amines, but it is still possible. So if you can control your number of products to be formed, then definitely we can use this. So then you wonder, what are these useful for? I thought they were most interesting compounds. They are very, very interesting reactions with nitrous acid. The most interesting reaction of nitrous acid is with aromatic amines, okay? And so here's what happens with an aromatic amine. Here's aniline, this is nitrous acid, and what you end up doing is forming a diazonium ion right over here. Okay, this is a diazonium salt. So once you have a diazonium salt here, remember NH2, that makes it a good leaving group now. Okay, that's exactly how it was in the primary amines that we did in the previous slide. So once this is a good leaving group, now you can start to do SN2 reactions on the benzene ring, which if you remember in aromatic chemistry, it was a major no-no. You cannot do SN2 reactions on benzene because benzene itself is a nucleophile. But now you have an excellent leaving group on the benzene ring. And so once you have this on there, you can do any kind of substitutions on it. Okay, and so this makes it a neat reaction as far as substitution on the benzene is concerned. So now whatever reactions you could not do before with benzene, now you can do this. Okay, so let's look at that. Here are all the reactions you can do. Okay, once you have an aniline, you treat that with HONO, nitrous acid, you get your diazonium salt, then you can treat it with any of these compounds and get very specific products. So for example, making phenol, we were not able to make phenol using substitution reactions. It really took drastic conditions to make phenol, and that also was the industrial synthesis that I gave you for phenol back when we did phenols. So now you can take a diazonium salt, treat that with copper 1 oxide, and here we go. Okay, here we have a phenol in presence of water, of course. The next three reactions are called Sand-Meyer reactions, and in this case you have substitution with chlorine, bromine, and cyano compounds. So here is chlorine and bromine on the aromatic ring. Now, if you're wondering why you would want to get chlorine and bromine like this versus just taking a benzene ring and doing halogenation on that, well, you could, okay? But all of these reactions here have synthetic applications, okay? Yes, this is a very scenic way of making benzene chloride if that's what you're trying to make. But yeah, you wouldn't use this. You would just take a benzene, treat that with chlorine in presence of iron 3 chloride. But this is something that you would do if you had other groups on the benzene ring also. Okay, so it has a synthetic application to it. We had not learned how to put a cyano group on the benzene ring. So this is how you would put a nitrile on the benzene. And remember how many things you can do with a nitrile. You can hydrolyze it, okay, and you can make benzoic acid, or you can reduce it and then you can get benzylamine and so on. Okay, and so very useful compound. Then we never also talked about getting iodine on there or fluorine on there. Now these are easy reactions to do, which were really hard to do before, so we would never talk about it, but now you can. And if you wanted to get rid of the amine, then you can do that too. Using a weak acid, phosphorus acid, and water, you can get rid of the amine group entirely. Okay, and so synthetically, it's very useful when you're trying to do multiple step synthesis, then these reactions turn out to be very useful. There is another useful reaction of this, which we'll talk about in a few minutes. But anyhow, let's look at these reactions individually now. So here are the Sandmeyer reactions, okay, where you have an amine and then you treat them with the nitrous acid, and this is the diazonium salt that you get, and then you treat them with the proper copper bromide, copper cyanide, whatever it is, and then you end up getting your products, okay, and so then you can, isolate them, work with them. So it's really neat reactions to work with, okay, and so you can control a lot, okay, by using this method. And we'll do some examples as we are going through this in class. Here is the reaction with iodine. Here is the reaction with the fluorine yet again. And then here's the last one with the phenol. So again, just a review for you. They were all there in the previous slides also. And then here also you go step by step to show you how all these reactions are done. Okay, so I keep saying, they are very good for synthesis, very good for synthesis applications and so on. So here's an example of how you can actually use it to make very specific compounds. Okay, so 3,5-dibromotoluene cannot be made directly. What is 3,5-dibromotoluene? It is this right here. So if you start with toluene, okay, so if you start with toluene and you want to make 3,5-dibromotoluene, you cannot. Why? Because the methyl group is an activating group. If it's an activating group, you will get orthopara substitution. So this is what you will end up getting, because this is toluene. And if you do bromination, this is the product you will get. You will not get 3,5-dibromotoluene. So in order to make 3,5-dibromotoluene, then you would actually use nitration. Okay, so the step coming before this one is you will take toluene, treat that with the nitric acid and sulfuric acid, get the nitro group, okay, reduce the nitro group to amine group, okay. Once you have the amine group, then you can go ahead and do bromination. Now remember, the ring is super activated, so you don't even need a catalyst, and now you can get the two bromines over here, okay, which is ortho to amine, which is exactly how it works because it's activating group. So once you have this, then you go ahead and treat the amine group with the nitrous acid. It becomes the diazonium salt, and then you treat it with phosphorus acid and get rid of your amine, and voila, here is your product. Okay, so this is like a synthetic application of these kind of compounds, okay, with the diazonium salt. So it's not just that you want to take the amine group and use it to make something else. You can do that too. However, this is another application where you really don't need the amine group at all. You just need it to do a synthesis. Okay, so yes, your synthesis is elongated, but at least you end up getting exactly what you wanted. Okay, so this is just one example of how you can use amines to have a very targeted synthesis. One other common reaction of the diazonium salts, as I said to you before, that I would mention is a coupling reaction. Okay, and a coupling reaction is when you have two things that are combining together to form a couple. And so here, if you have a diazonium salt and you treat it with another aromatic compound, a nicely activated ring, then instead of getting a substitution or anything like that on the benzene ring, you actually get what is called a coupling reaction, which means that the nitrogen and the nitrogen here, the nitrogen here, I should say, will combine with this carbon over here, which is the activated position if you have an electron donating group. So then you end up forming this kind of a compound, which is called a diazo compound, okay, because now you have two nitrogens over here. So these have their own functionalities, and I don't know if you can remember this or not by just looking at this. You saw this in the previous presentation with a lot of dyes. Okay, so a lot of these dyes, they have diazo linkages, okay, in them, and so this is called a coupling reaction, and there's a coupling reaction. So this is how it works, okay, where you just have diazonium salt and you treat that with a phenol or any other activated ring, okay. So here are some examples of how this works. So if this is a diazonium salt and here is your activated ring, now remember this para position is taken, so then ortho position will then be coupled, okay, with the diazonium salt. And then we talked about, was it methyl orange? Okay, we talked about that. So you can form methyl orange that way, and here are some other, here's another example. Okay, this is orange too, which is made from naphthol. So depending on what kind of dye you want to make, you can choose different kinds of rings, different activated rings. And these are very useful compounds. They're all dyes and, you know, they make our life colorful. So it's really very good. Coupling reactions were actually discovered by a medicinal chemist and not really a organic chemist as such, but he was a medicinal chemist looking for a medicine. And so he ended up having an accident in his lab. And yeah, serendipity is good, but you also have to be observant in order to make a big discovery. So here are some problems. Go through this on your own. We can talk about it in class also if you want. So these are, you have to fill in all the reagents in this, see if it works out for you. We can again bring it to class and we can go over it. So from this chapter, please know all the synthesis of amines. I know there are a lot, but a lot of them are just reductions and a lot of them you've done before, okay? So please go through all of those, including the rearrangement and all that. The reactions of amines, yes, you do have to know the reactions of amines also. The diazo reactions are by far the most important reactions of amines, but some of the other ones that we've talked about are also important, okay? So again, the diazonium salts coupling reactions, and all your aromatic synthesis that we did so far back away. Please review that again, because again, you will be using all of those concepts, okay, in this chapter.